Good afternoon, my fellow intellectuals. So today we're going to be dealing with equation on rotational motion. It can be rotational or circular motion. Coming all the way from the University of Zambia. I'm not sure if it's a tutorial sheet question, but it came from some guy from UNZA. So if you want me to solve any practice problem in any of the sciences or bar, I can solve it. You simply have to send it in pictorial form to 0978957975. So when you send the question to this number, I can be able to solve it, and then I can make a video like this, or I can send it directly to you. So the question says a small sphere of mass 0.5 grams is suspended by a string 5 centimeters long, with the string kept taut. The bow is whirled in a horizontal circle of radius 25 centimeters. Calculate its angular speed in radians per second. So first of all, when you look at this problem, you have to create some sort of diagram. That's how we solve physics. We have to write a pictorial form of the diagram. Already it has been written in the question, but then we have to also write it down so that we can draw various things from there. So first of all, we write down our data, which is the data that we've been given. So we are told the mass of the sphere is 0.5 grams. 0.5 grams is the same as, we can convert this one, 0.5 times 10 to the power negative 3. That's 5 times 10 to the power negative 4 kg. And then the other thing that we've been given is the length of the string. Length of the string is 50 centimeters, which when you convert to meters is 0.5 meters. And then we also have the radius, which is 25 centimeters, which can be 0.25 meters. So now the good part about writing your data is you attract yourself some marks, and then also you will know what you have so that you can get what you don't have, because that's what physics is all about. It's finding what is unknown using the knowns. So we can go ahead and write our diagram. This is our mass, and then when you look at it from a radio perspective, this thing is going like that, but then when you look at it from above, it's going like this. So it's sort of making a circular path. So now to get right into it, first of all, we are going to find the tension force in this rope, so that the tension force can now allow us to find the velocity. So we are going to use this equation, F is equal to ma, and then if the force is centripetal and then the acceleration will also be centripetal, then we are going to be having the force being equal to, since the acceleration is equal to v squared over r, the force will be mv squared over r. And then since we have the radius and the mass, we can find the velocity. Immediately we find the force. So now the force will be the force that is centripetal, and also that we're going to have some centripetal acceleration. So now first of all, this one we are going to resolve the tension force into its components, because it's moving in the x direction and also in the y. So now we can also write this one down. We can write it again. because we don't want to mess up this one, of course. So we have our tension there, then we have our theta, and then we resolve our force in components. So we're going to have the downward force, mg, and then up we are going to have the force that's due to this tension. Since this tension is a vector, so it has a y component and an x component, and also a component there. So now this theta is the same as the theta that's being made there. So now if you want to find this vector here, the force in the y component, it will be the adjacent to this theta, which is t cos theta. Since when we make this one as a triangle, it will be like this, and then like that, where this is this one, so if this will be our theta, then this will be our t, then t cos theta will be equal to the thing that's there. Since this one is adjacent to this one, and then we know from Sokatoa Ka gives us the cos of theta is equal to the adjacent over the hypotenuse, which is t. Then when you make the adjacent the subject of formula to be t, the cos of theta, which is what is there. And then this one will be t sine theta, because this vector here is the same as a vector that we can draw there, and since it's opposite, it will be sine. We can go down to from Zokatoa, we have so, which is sine is equal to sine theta is equal to the opposite, which is what we are looking for, the opposite over the hypotenuse, which is t. When you cross multiply, we'll be having the opposite being equal to t sine theta, t sine of theta. So now in our equation, when you look at our data, you've not been given theta, so even if we sum up the forces, this will be an issue for us. But then we've been given the length and the radius. So when you look at this one there, it's like this. We have our mass there. So now we have been told that this radius is 25 centimeters, and then this one is 50 centimeters. So now we can easily find this one. We can easily find the theta there, because we have this and this, and so this theta will give us the same theta that's on the other side. So now since we have a side that's opposite and the hypotenuse, we can use the sine. So it will be sine of theta for this one is equal to the opposite over the hypotenuse. Now we can use the meters so that we can have everything in SI units. So the sine inverse of the opposite over the hypotenuse will be equal to the theta. Since when we take the sine inverse of both sides, this one will cross out, and then we have theta on the other side. So now our theta will be equal to the sine inverse of the opposite. The opposite here, the opposite is 25 over 50. So now this is just like half, and you know sine inverse of half is just 30. We can try to counter check with the calculator. So 25 divided by 50, that's 0.5, and then we have sine inverse of the answer, that is 30. There's an easy way that you can use to memorize these, and you can actually find them even without the calculator. I'm going to make the video, just make sure you subscribe. When I make the video, you're surely going to see it. So now we have such values there. So now we can go on from here, since we found the theta, and then we can I can use this for reference. Yeah. So then since we have from when you look at this one, we have our theta now. So now we can sum up the forces. We can start with the y direction. You can start with the x or the y, but it would depend with actually what you're looking for. For this kind of problem, I'm going to advise you to start with the y direction. You will see why in a few minutes. So now you can sum up the forces, or summation of forces in the y. When you look at this one in the y, we have two components. We have t, and then we also have mg. Now mg, when we take down as negative, mg will be negative. Thus we'll have t cos of theta minus mg. Now summation of forces in the y is equal to mass times acceleration in the y. Now when you look at this mass, it's not moving in the y direction, it's only moving in the x direction, not in the y. So now we can conclude that acceleration in the y is 0, since there is no movement at all. So now acceleration in the y is equal to 0. Thus summation of forces in the y is equal to 0 as well. So now we can put our 0 there, t cos theta minus mg. So now making t subject to the formula, because t, that's the force that we are looking for. So we have our t cos theta is equal to mg. When you take mg that side, and then when you divide both sides by cos of theta, and then you're actually multiplying by 1 over cos theta, then to give you this, then you can cancel that out. Then you have t being equal to mg over the cos of theta. So now you can now go to the x direction, knowing that you have m, you have g, and you also have theta. So you can find the t, but then in physics it's actually advisable that you don't keep finding figures anyhow, because you're going to lose, because you keep approximating, or you keep on taking to some significant figure when you get a big number. So the answer goes on losing its accuracy. So you can label this as our equation 1. But I'm going to show later how you can actually find the same answer even if you actually keep plugging in the values. But it's better to use symbolic answer. So this is the symbolic answer for a tension force. So now when you go to when you go to the x direction, now we are going to have we don't have we only have one. We don't have any going out. We only have this force. And then now this force, when you look at it carefully, it's actually the centripetal force, because it's actually the force that's going that way. So now you can say the first summation of forces in the x is equal to t sine of theta, and then summation of forces in the x is equal to ma in the x. But then acceleration in the x is the centripetal acceleration that's there. So now you can go on, since this is equal to that, we have t sine of theta being equal to ma x. Then when you make t subject to the formula, you're going to have t sine theta over ma x multiplied by 1 over the sine of theta, both sides, sine theta. So now you can cancel out the sine this side, so then the t sine the t, just the t rather, the t will be equal to the mass m x over the sine of theta. Now remember, this acceleration is actually centripetal acceleration, so t is equal to m over sine of of theta, centripetal acceleration. Now you know to say centripetal acceleration is equal to v squared over r, the equation that I told you earlier. We can now use it here, and then it will help us find the velocity. So now we can plug in that there. T will be equal to m over sine of theta times v squared over r. So now we're going to be having t being equal to m v squared over sine theta r. Now when you look at this t, it is equal to this one. This is the t, this is the t here, this is our equation 2. So now we can equate these values. So even without finding the figure for t, you can actually find that you can actually solve this one, which will help you and will reduce the complexity of your question, and you actually find the answer quicker than possible. And then also, if you made the mistake here, it will affect your problems entirely. But then for the symbolic answer, even if you make a mistake in plugging in the values, you actually have the correct symbolic answer. So you've been correct all along, and then only in the final part you're going to be wrong. So you're going to attract yourself a lot of marks when you're dealing with problems. So now you can equate our mg over cos. Okay, you can write this down. Equating equation 1 and equation 2. So now this mg over cos theta is equal to mv squared over sine theta. You can put the r aside, and then you're going to notice something. We have common values here. We have got the m there and the m there. So when we multiply both sides by 1 over m times 1 over m, the m is going to cancel out. So we're going to have g the cos of theta being equal to v squared over r sine of theta. Now here you're going to notice that the mass is actually not the velocity does not depend on the mass, because the mass is not actually in the equation for the velocity, which is actually something that is good, which is also actually something that is true for an object moving in centripetal motion. So now we make v the subject of the formula here. So we have we can cross multiply this, we'll go there. So we're going to have v squared being equal to r sine theta. We have our g, this g that's there, over the cos of theta. So now this value here, sine theta over cos theta is tan theta, so v squared is equal to r. You can put our g there, then tan of theta, then we'll take the square root of both sides, find the velocity being equal to rg tan of theta, which is our symbolic answer. Now this velocity does not depend on the mass, so now we can actually go ahead and then plug in the values, and then we are going to find the velocity. So now we are saying our v is equal to we know very well that our r is according to our data there, our r is 0.25, so we have our 0.25, and then our gravity is 9.8 near the surface of the earth, then our theta is 30, and then that's all. You are going to find the velocity, although it's not actually the end of the problem. So now we can say 0.25 by 9.8 by the tan of 30. So that's our answer. Then you take a square root of the answer. That's our velocity will be 1.189. We can just leave it there. 1.89 meters per second. Now our question tells us to find our angular speed. We have the speed, but then we want the angular speed. But then this actually is easier because our velocity is equal to the angular speed times the radius. So now when we make the subject formula, the angular speed, we are going to multiply both sides by 1 over r times 1 over r. So we're going to have our angular speed being equal to v over r. Then our angular speed will be equal to 1.189 meters per second over our r. Our r is 0.25. So now when you divide this one, you divide by 0.25, you're going to have 4.76. We can put it to 3 significant figures, rads per second. So now this is our final answer. Now I told you that I'm going to show you a way in which even if you find the figures, you will actually come to the same answer. So let's say if here at t we found the figure, so t is equal to m is 5 times 10 to the power negative 4, from our data 9.8 over cos 30 times 9.8 divided by the cos of 30. Thus our tension is 5.66 times 10 to the power negative 3. Now see that we rounded off here, so our answer keeps deteriorating. So that's our force. And then we can, from this force, you can actually come here where we are saying that this same force is equal to T mv squared over sine theta r. Then you take the t is equal to mg wait a minute, for this one with a tension, force, you can, I think we can actually go from here. We can actually find something, mg over the cos of theta. But then for this one, specifically for this one, we've already found this figure. So now these m's will not cancel. Yeah. So now we're going to just find we're going to just make v as suppose a formula here. So we're going to have when you cross multiply, t sine theta r is equal to mv squared. When you divide both sides by m, you're going to have your v squared being equal to t sine of theta r over m, square root of both sides. Our v is equal to t sine theta r over m, the square root. So now our v is equal to t is t we found it to be 5.66 times 10 to the power neg, this was neg 3, sorry for that, this was neg 3, sine 30, our radius is 0.25, of course, and then our mass is 5 times 10 to the power 4 kgs. So then our velocity will be equal to 5.66 exponent neg 3 times sine 30 times 0.25, then divide by 5 exponent -4, and then you find the square root of the answer. So we found our velocity to be 1.1895 this time meters per second, which is exactly what we found last time. So now you see that this one will actually make your work harder, because imagine if you make a mistake here, then the answer will be affected. But then if you come very well here, then you make your mistake here, you are actually correct all along. And then of course you can use either method that will be easier for you. So that's all for this problem. For me it's bye bye. Remember to subscribe to the channel and then send your questions to 0978957975. Don't worry about this number, it will be flashed on the screen, of course.